Yeah, thanks. Yeah, so I'm Shomik. This is Firas. We're both PhD students at Stanford working with Mate. So yeah, we're talking about Sparser, fast analytics on raw data by avoiding parsing. So the motivation for this talk is, we're processing bigger unstructured data sets, and hardware is getting increasingly fast. But despite this, we kind of found that parsing unstructured data before querying it is often extremely slow. And if you look at the Spark ecosystem, there's actually some recognition of this, and there's actually solutions to partially solve this problem at least. And in particular, Spark has this data sources API that allows you to push part of a query into the data source. So logically, the data source API sits beneath the core Spark engine. And basically what it does is it allows you to push like a SQL query down into, say, a Parquet parser or an Avro parser. And it allows you to do things like prune columns in Parquet, so you only have to load data into like an RDD if you're actually going to use the data from that particular column, for example. But kind of the bad thing about this API as it stands today is that there's little support for unstructured formats or like textual formats such as JSON. So as an example, you can't avoid JSON parsing using the data sources API, and that's kind of intrinsic to the format because there's no way to prune out a single column or project a single field in these formats. Parquet is kind of designed to support these kinds of operations, but formats that people use like JSON and CSV are not. And it turns out that parsing these formats, such as JSON and CSV, is actually a huge computational bottleneck. In particular, we found that existing state-of-the-art JSON parsers are over 100 times slower than just scanning a string. Right? So this plot on the right is showing two really fast JSON parsers, rapid JSON. So you can think of that as like Jackson, which is the parser that Spark uses. And then Myson is this new research parser that Microsoft announced recently. And if you compare the time of parsing a 5 kilobyte record, it's much, much slower than just scanning through that record in memory, which you would kind of expect, but at the same time, newer formats like Parquet are kind of optimized to be parsed at similar to the speed of like scanning through memory. And believe it or not, we actually found similar but less dramatic results on some binary formats. So sometimes in certain cases, parsing things like Avro and Parquet is also prohibitively slow. So it takes a long time just to load data into, say, an RDD or a data frame. Okay, but parsing kind of seems to be a necessary evil, right? Like, how do you actually process data before parsing it into, say, a Java object or something? So how do we actually get around this? So one kind of key opportunity is that many queries actually exhibit high selectivity. Or in other words, they actually just rely on a really small portion of the total data set. And this is especially true for exploratory analytics, where you're just kind of looking around in your data and looking for patterns. And to exemplify this, I have kind of two case studies here. So we found that 40% of the customer Spark queries at Databricks, and specifically over data on JSON and CSV files, select less than 20% of the data. And 99% of the queries in Census, which is this system for performing port scans over the internet, select less than 0.001% of the data. So if you have these massive data sets, you're only actually looking at a small portion of them every time you make a query, it's actually really wasteful to go through and parse the whole thing. And as it turns out, this data source API we saw before actually provides access to the query filters. This is kind of one opportunity that we can use, especially in Spark, to kind of speed up parsing these big data sets. Okay, so how do we actually do this? How do we exploit high selectivity to accelerate parsing? Well, that's kind of the main idea of Sparser. So in Sparser, you filter data before you parse it. Okay, so that's kind of the crux of the system. So while today you have this giant raw data set sitting on disk or in memory or whatever, and you go through and you parse the entire input, with Sparser, you apply these fast but approximate filtering functions that produce false positives and no false negatives. And all this filtering function does is that it looks at this raw byte stream and it throws out bytes that it knows you aren't going to need in your actual application based on whatever query predicates you're providing it. Okay, and in Sparser, instead of applying just one of these approximate functions, you can actually apply a cascade of them and make your raw data set, so this is just like a raw byte stream, smaller and smaller. And finally, you're left with something much smaller than what you initially started with, And you can actually use your usual parser, like Jackson or whatever, to parse this, get your records out, and then apply like your actual predicates to throw out any false positives that might be left. OK, so just to show an example of kind of what Sparser can give us, we're going to do a quick demo. And in the demo, we have a data set of tweets. So each tweet is a JSON record collected using the Twitter Stream API. And we're going to find tweets where the text of the tweet contains Trump and Putin. OK, now actually not going to do this demo in Spark. We have a little dummy REPL here set up just to kind of show the raw performance. And a little later in the talk for us, we'll talk about some results in Spark. OK, so we have this 24 gigabyte data set of JSON records, and I've kind of preloaded this SQL query in here. So we're just counting the number of tweets where the text field of the tweet contains Trump and Putin. OK, so this data set is like, it's each line of the data set is a JSON record. So to answer this query, we first have to parse every record and then get the final count. OK, so I'll hit 1. So this is going to run the query with Sparser. And then it's going to run it with rapid JSON, which is one of these kind of best-of-breed C++-based JSON parsers. OK, so this should run for a couple seconds. OK, there you go. So that took around 13 seconds with Sparser. OK, and now it's going to do it with just rapid JSON. And we'll actually come back to this because it's going to take some time. OK, so logically, Sparser fits into Spark SQL as follows. OK, so usually when you're reading some data into Spark, you can pass this format thing in, and that's just telling Spark what kind of data to expect. So Sparser kind of fits in below the data source API. So it's actually implemented as a part of the data source API. So you can just specify this special format, edu.stanford.sparser. Whatever format. We actually support Avro, Parquet, and JSON, and also CSV. And that'll automatically cause the data source API to call into our filtering engine. OK, so it's really just a one-line change if you want to use Sparser in your Spark applications. OK, so let's do a brief overview of how Sparser actually works. So Sparser's main kind of construct is these things called raw filters, or RFs. And so RFs are basically these filtering functions over a raw byte stream that produce false positives but no false negatives. And then we use an optimizer to combine RFs into a cascade. So as we saw earlier, we can actually compose a bunch of these raw filters into a sequence and basically get more effective filtering. OK, to illustrate this, let's look at this dummy query again. So we're looking at tweets where the text of the tweet contains Trump. So here's a potential RF. OK, so what this RF is doing is it's looking for the substring Trump. OK, so notice how we're not actually looking for the whole thing Trump. We're just looking for a substring. So this clearly can produce some false positives. But it's not going to produce any false negatives because if we don't find Trump, we're definitely not going to find Trump. OK, so now we have this raw byte stream coming in. So all this RF sees is the sequence of bytes. And then you can see here that the byte stream actually does contain Trump, but it doesn't contain Trump. So the RF will pass. OK, so this is just going to allow the bytes or this record to kind of pass through the RF. Right? But like as I said, we don't know that Trump appears in the text field of the JSON record. We don't even know if we've seen the entire word Trump. And in this case, we did come up with a false positive. So we can actually chain these RFs together to decrease the false positive rate, and then apply the full parser only on the bytes that actually remain at the end. OK, so there's a few challenges in actually building a system around this idea. And kind of the first main challenge is that we need to implement these RFs efficiently in some sense. Right? So they're basically these approximate filters. They have no notion of what a data format is. They're just looking at this sequence of bytes. So if we do something kind of stupid, then we're just going to spend time like inspecting a byte stream, and then we're going to end up having to parse the entire data set again anyways. So it's critical that these things are efficient and that they actually discard data effectively. OK, which kind of leads into a segue to the next point, which is how do we actually efficiently choose the RFs to maximize parsing for a given query and a data set? Right? So in the previous example, I showed Trump as a potential RF. How do we actually come up with that one, and how do we know that it's a good potential RF to use for our data set? Right? So if our data set has Trump in every tweet, then maybe that's not a great RF to use. Whereas if we only see Trump like 1 or 2 times, or only in tweets where Trump appears, then that's a great RF to use. OK, so in the rest of this talk, I'm going to talk about Sparser's API. So this is the kinds of queries that we can actually support in SQL. I'll talk about how the raw filters are designed. And then for us, we'll talk about the optimizer, which is how we choose a cascade, and also give you guys some performance results on a variety of file formats. OK, so let's see if this thing finished. All right, so there we go. So that's around a little more than a 10x speed up, I believe. A little less, I suppose. So it does give you these substantial benefits, and of course, it does give you back the right answer, because the false positives are kind of only hidden in the system. They don't appear in the final result. OK, so I'll talk a little bit about Sparser's API. So Sparser supports exact string matching, so things like user.name equals Trump, likes equals 5,000, things like that. It supports substring matching. It supports whether your data set has a particular key. And it also supports conjunctions and disjunctions of these things. Kind of critically, Sparser currently does not support numerical or range-based predicates. And I'll talk about the design of these RFs next, and it will kind of be clear why we can't support these. And just a note that these queries actually work over both textual data like JSON, and that's the example I'll be using throughout the talk. But they also work over binary formats and compressed formats such as Parquet or Avro. OK, so how do we actually design these RFs to be efficient? And kind of the key thing that we do is we use these SIMD-based filtering functions that pass or discard records by inspecting a raw byte stream. OK, so SIMD is basically a feature that modern CPUs have. It basically allows a CPU to process multiple bytes of input data in parallel, usually in a single or a handful of cycles. Right, so usual CPU registers are 64 bytes. A SIMD register might have something like 32 bytes. So it's basically a way to get parallelism within a single core of a CPU. OK, so we saw something similar to this plot before. This is basically showing the cycles per 5 kilobyte records it takes to parse a JSON record. So rapid JSON and MySON take tens of thousands of cycles, but applying a single SIMD-based raw filter to see whether there's a substring in there that we're looking for takes 2 orders of magnitude less than that. So if we can find a few of these RFs and discard 90% of our records, that's going to give us some pretty substantial performance benefits. OK, so just an example of one RF that Sparser supports. Kind of the most basic one is just looking for like a substring of your query. OK, so the substring search RF is just going to search for a small 2, 4, or 8 byte substring. And the substring is kind of based on a query that you're passing into your system. And the search is done using SIMD. OK, so as an example query, let's look at text contains Trump again. So this scary-looking image is actually just showing how this RF will execute. OK, so we have some input text. It kind of resembles JSON. Just notice that it says, I just met Mr. Trump and not Mr. Trump. So we're going to see another false positive here. And what these shifts indicate are SIMD registers. So in a single register in the CPU, we're packing this string Trump and repeating it over the entire register. OK, and now what we can do is we can do these comparisons. So we're comparing byte by byte, and we're shifting it 4 times so we can find all potential matches until we see Trump. OK, so in the 4th shift, we actually saw that the TRUM in this image match up, so the RF passes. OK, so again, this is producing a false positive because we haven't actually checked if the string says Trump. We actually found Trump. But again, there's no false negatives since no Trump implies no Trump. Right? So if we hadn't found Trump in this input, we could kind of safely throw away the whole record. OK, so on modern CPUs, we can actually compare 32 bytes in parallel in around 4 cycles. So this entire routine of checking a 32-byte sequence and throwing it out if we don't find anything can happen in 2 nanoseconds, which is pretty fast. OK, and there's also other RFs possible, and Sparser kind of picks them in its optimizer, agnostic of how they're precisely implemented. OK, so Firas will take over, and he'll talk a little bit more about how we actually choose these RFs and give you guys a summary of the performance results.
Cool. Thanks, Shomik. Can everyone hear me? OK, I think it's on, yeah. So as Shomik said, one of the key challenges once you've decided how to implement these RFs efficiently is to sort of choose the right RFs, determine which RFs will give us the fastest parsing time. And this can be tricky because there's sort of 2 different factors you have to consider: the runtime cost of the RF and the false positive rate. So to decrease the false positive rate, the first thing we do is that we combine multiple RFs into an RF cascade, right? And here are 3 different examples of that. So on the left-hand side, you have a cascade with 3 different filters, right? And this is kind of the example that you've seen earlier, where you apply one RF after another until you get a smaller portion of the raw input, and then you apply your full parser to parse that. This middle example, though, is a case where we have a bad cascade. So we've got 3 different raw filters, but the false positive rates are all very, very high. So as a result, very little gets filtered from the raw data, and now you're forced to parse the entire raw input. And then this last example on the far right is an example of sort of the optimal cascade, where you've got a single RF that filters the exact same amount as the one on the left, but because it's a single RF, it has a much smaller filtering overhead. So the right-hand side is kind of the ideal, but most importantly, you want to make sure that you both balance the false positive rate so that it's very, very low, and also minimize the filtering, the RF execution overhead. Okay? And the second question is, how do you actually generate these cascades? And in Sparser, we use an optimizer to find all the candidate cascades and then pick the best one. So how does this optimizer work? Well, at a high level, it sort of proceeds in 4 different steps. The first step is we take the user specified predicate, and then we generate all the possible RFs from that predicate. And then, once we've got all the possible RFs, we take a sample from the raw input, and we measure some cost parameters that will help us then extrapolate what the full cost, the full execution cost of the RF cascade will be. Once we've made those measurements, we score and choose the possible cascades, we pick the best one, and then, of course, we apply the chosen cascade to the raw input, apply the RFs, and then send the filter bytes to the full parser. So at a high level, it's these 4 simple steps. And let's go through them one at a time just to make sure everyone understands. So for the next several slides, we're going to use this running example of names equal to Trump and text contains Putin, or names equal to Obama. This will be our running example query to sort of illustrate how the optimizer works. So the first thing we do is we generate all possible RFs. So in this case, we'll generate 2, 4, and 8 byte substrings of Trump and of Putin and of Obama. Now, one caveat here is that doing this translation from the predicates to the RFs is often format dependent. So for example, if you're doing this in a binary format like Avro, you may have to apply something like zigzag encoding to make sure that the predicate actually corresponds to a correct RF, so that you search for the correct bytes in the raw input. Right? Now, in this example and for this talk, we're just going to talk about JSON. And if you're more curious, you can check out the details in the paper. But the most important point I want to stress is that once you've done this sort of format-specific conversion from predicates to RFs, and once you've figured out how to delimit your data inside the input byte stream, the rest of the entire process is format agnostic. And this is the reason why Sparser can generalize to multiple formats, not just JSON and CSV, but also Avro and Parquet. Okay, so we've done that. We've generated the possible RFs. The second thing we do now is we sort of evaluate the RFs and we measure certain costs, certain parameters of the RFs on this sample of records, a small sample. And we also do the same thing for the full parser that we're going to delegate to at the very end. The 2 things that we're going to measure are the pass-through rate for each RF, and of course for the parser, which is going to be a pass-through rate of 1 because it passes everything, and the runtime, the execution cost of each RF, and the full parser. Okay? And so once we measure the individual cost of each of these different components, we can then extrapolate and calculate the full cost of a cascade. Now, but doing so is actually a little bit tricky. You can't just naively combine these by doing simple multiplies and adds. Because the truth is, the pass-through rates of the RFs are actually not entirely independent. So for example, let's say you pick the RF Trum, T-R-U-M, like Shomek was saying earlier. And then you also decided to add a second RF as part of your cascade, which would be rump, R-U-M-P. The likelihood that you find trum and rump in the same byte stream is actually fairly high. It's going to be very correlated, so it's not a good idea to combine those 2 RFs. You're not going to get much additional benefit by adding rump to trum, basically, right? But on the other hand, you can't measure all possible combinations of RFs, because that would be a combinatorial search problem, and it would take very, very long to figure out which one is best. So the way we kind of get around this is we have this non-independence problem, but the solution is actually a pretty simple one. We use bitmaps. So what we do is, for each sampled record, we have a bitmap per each candidate RF, and then we set the bitmap index 1 to be true if a particular record I passes that particular RF, right? And so what ends up happening is you have a bitmap per RF. The bitmap's bits are turned on if a record in the sample passed for that particular RF. And then if you want to find the combination of whether 2 RFs match for that particular sample, all you have to do is just do a bitwise AND. So I can very quickly compute the probability of 2 RFs by taking the bitmaps of each and then just doing that simple bitwise AND. And that gives me the ability to sort of explore the combinations much more efficiently. Okay. So once we've done that, now we're on to step 3, choosing the best cascade. Okay. And again, we've got this running example, names equal to Trump, text contains Putin, or names equal to Obama. So here's an example of a valid cascade. And the way you want to think of a cascade of RFs is actually as a binary tree, where the leaves of the tree are either a discard or a pass action, right? Whether you discard or pass the record. So here's an example of a valid cascade. First, we run Trump. If it fails, we go to Obama. Otherwise, we go to Putin. And then at the very end, we go to Obama if that fails. Okay? Here's a second example of a smaller cascade. You notice that Trump is no longer in this one. It's just UTIN or OBAM. And that's OK, because in Sparser, false positives are acceptable, right? But this third example is an example of an invalid cascade. And the reason why is if you look at the path from TURM to UTIN and then the discard, there's no point at all in that path where you actually hit OBAM, the Obama predicate, right? And this is important because we have an OR clause here, or names equal to Obama. If you went down that particular traversal from TURM to UTIN and then the discard, you might actually forget to check for names equal to Obama, right? And more generally, what you have to do when you generate these cascades is you have to make sure that every single path from the root of the cascade tree to a discard has to always make sure it hits at least one RF from every single OR predicate, every single disjunction in your query. Once you satisfy that requirement, then you have a valid cascade. Okay. And then, of course, to compute the cost of that cascade, you just traverse the tree from the root to all of the leaves, and we use these runtime measurements and these pass-through rate measurements that we took from the previous step to then calculate the full cost. Algebraically, what this looks like is this following formula. It's actually not that scary. So if C sub R is the cost of our cascade, then all we have to do is take the sum of probability of executing that particular RF times the cost of that RF, sum of all of those, and then, of course, at the very end, do the same thing but for the full parser. The probability of running the full parser, which is going to be 1, of course, multiplied by the cost of running that full parser. So just to make sure you guys understand, here's again that same example from the previous slide. And so what we'll do is we'll start from the top, and then we'll calculate the probability and the cost. We'll do the same thing for the subsequent levels, and then these levels, and then we go all the way down. We sum these all up at the very end, multiply the cost along the way, and we've got the full cost of our RF cascade. Yeah. And just to make sure that this is a sort of simple sanity check, we limit the depth of the cascade to be a depth 4 at most. We found in practice that anything beyond 4 will never give you good performance because then the filtering overhead is just too high. So, yeah. Makes it easier for us to also just make sure we don't explode in sort of the combinatorial search space as well. So that's sort of like the in-depth tour of the optimizer. Before I jump into the performance results, I want to talk about, of course, the Spark integration so that you guys can use this as well. So Shomik showed you this slide earlier, kind of the high-level architecture of how Sparser fits in with Spark. Let's kind of dive in deeper and see how it exactly works. So basically, it's actually very simple, and you as a user don't have to do anything different. All you have to do is swap out your format with edu.stanford.sparser.json, Avro, Parquet, CSV, whatever. But the way that it works, if you're curious, when you specify that Spark SQL query, what the Spark package for Sparser does is it extracts out the predicates that are Sparser compatible, and then it passes it down into our C++ code. At the same time, we read the raw data from HDFS. We take those predicates that are Sparser compatible. We then do the same thing as before. We generate the RFs. We run it through the optimizer. We find the proper cascade. And then we pass it through. We filter it. And then it generates a series of sort of unsafe rows, which then get turned into a Spark data frame. So at the end of the day, you as a user, if you want to use Sparser with your workloads, you'll get the exact same data frame that you would get normally with Spark plus Jackson, just get it faster. So there's no difference to you. All you have to do is swap out that format that you're going to read from. Okay, cool. So finally, let me talk about some performance results before we close for questions. So in our evaluation, we benchmark Sparser. We sort of picked two major data sets. The first is that census data set that Shomik mentioned about, that was a sort of a search engine for internet port scan data. And then we also collected a bunch of tweets. We benchmarked our Spark experiments using a 20-node cluster on Google Compute Engine. And then we also had some single-node experiments with a very beefy Intel Xeon machine. So we ran 9 different queries on JSON data from Census, 652 gigabyte JSON data. And these are our end-to-end Spark experiments. So what we did is for each of these 9 queries, we benchmarked the end-to-end runtime of loading the JSON data from disk, parsing the query, and then running all the filters, all of the group bys, all of the aggregations in that particular Spark SQL query that the user was running. And as you can see from these results, across the board, Sparser speeds things up quite a bit, as much as 4x end to end. And if you notice, there's two things I think that are actually really interesting. One is that once you combine Spark with Sparser, the total runtime is actually not much faster than just loading the data from disk. So we've heavily reduced the amount of time you spend parsing. And if you also notice, this kind of goes back to Shomik's first point at the very beginning of the talk, the query itself, where you're actually doing the filtering or you're doing the aggregation or the group bys, it's usually actually not that expensive, right? Granted, these were somewhat simple queries, but in general, for most exploratory analytic workloads, it's not going to take that much time. In fact, most of the time is spent parsing, but with Sparser, that's not the case anymore. We did the same thing also on our Twitter data set, and likewise, we get actually a 9x speedup in the case of Twitter. Once again, Sparser reduces things quite a bit in terms of query runtime, and it's not much overhead compared to just the time loading that JSON data from disk. Now, we also just did some benchmarks on that single node, like I talked about, and we compared things just in C++ land. So if you take Sparser and then combine it with RapidJSON as the full parser, or you take Sparser and combine it with Myson, this research project from Microsoft, once again, you actually see significant improvements compared to not having Sparser. And in fact, in this case, it's up to a 22x speedup. And for this particular experiment, we compared against, again, the 9 census queries. So across the board, Sparser actually helps quite a bit. And then finally, as we talked about, Sparser isn't just for JSON data or CSV data, it also works on binary formats. And granted, the speedups aren't quite as good, and that makes a lot of sense because parsing these binary formats is actually very efficient. For those of you who have worked with Parquet and Avro, you know firsthand. But even in that case, when we're benchmarking these Twitter queries, we saw that for Avro, we saw up to a 5x speedup, and for Parquet, we saw up to a 4.3x speedup. So in conclusion, Sparser is this new parsing engine that Shomik and I have worked on, and it uses this raw filter construction to make parsing very efficient. We filter before we parse. We use an efficient optimizer that selects the proper raw filter cascade so that you guys can parse things very efficiently with very little overhead. And it delivers up to 22x speedups over the existing state-of-the-art parsers for JSON and can generalize to binary formats too. We're working on open sourcing the code soon so that you guys can take advantage of it, but for now, we're happy to take your questions.
You mentioned this will work for Parquet as well, so does it actually work right now, or can I just swap out the format with, like, how would I read that for Parquet files?
So for Parquet, you just say edu.stanford.sparser.parquet, and it should work.
Everything else the same?
Yeah.
Okay.
Yeah.
Why this technology is applicable only to unstructured data? Can it be applied for structured data as well?
Yeah, so I guess the Parquet and Avro data sets are also, in some sense, structured data formats. They just have a bigger effect on unstructured data because, I mean, just by construction, they're more difficult to parse. But yeah, they do work on things like Avro, and the speedups there basically come from not having to look into each record. You could do this fast scan, and if you find something that could match, then you actually go down and like recursively traverse the schema and extract values.
You will see more speedups on the unstructured data though, because in those cases, the parsers tend to be a lot slower because it's unstructured. Because it becomes this very complicated state machine process that requires a lot of logic, and you can't do lots of parallelization. Like Shomik said, in the structured case, it's much easier to parallelize and much easier to parse quickly because you can take advantage of that structure.
Yeah.
So, Tim Kraskan's their team has done some work on memorizing the entire data set and applying models to eliminate filters and trees. Have you guys compared it, or thought of comparing it with your technique?
Yeah, so I mean, his work is kind of similar in spirit, and in some sense, it could use something like this as well. We're kind of more focused on if you have like, you know, some raw kind of data set that you just want to like query into quickly. Whereas his is more if you were making repeated queries over the same data set. I mean, in that case, you could also just like load it into memory or do like a one-time conversion from, say, JSON to Parquet or some other fast format as well. Yeah.
Sure.
Have you thought about incrementality? Suppose you have already executed some queries and you have the parse results and you get a new query. Can you leverage the previous results?
Wait, sorry, could you repeat the question again? I didn't quite catch it.
Yes, so I'm asking about incrementality. So let's say you have already executed some queries and you have parsed results from those past queries, and now you get a new query. So can you leverage the past results?
Yeah, that's a good idea.
Yeah, that's a good question.
Yeah, so there's a lot of past work already on actually building up like incrementally parsed values and then reusing them. So this work is kind of one layer under that. So when you actually need to parse data, you could use something like this to filter out values that you don't need. But once you've parsed values, of course, you should just reuse them instead of parsing them a second time.
So in some sense, your question kind of hints at the fact that this work is complementary to those ideas, I think. So you can imagine applying Sparser to that to this workload, and then once it's done that filtering, then building an index so that it could be incrementally queried for subsequent work.